He's an extension engineer. Oh. Let's start over. Today we are going to talk about managing field operations to reduce energy costs. Our speaker today is Mark Hanna, extension engineer with Iowa State University. With that, we'll send it over to Mark.
Thanks a lot, Scott, and my apologies to the group too for not having these slides loaded in a timely fashion. It always works at rehearsal for me, and then something goes awry. But anyway, let's get right to it. There we go. Okay. Just a little bit of background here. I work in the state of Iowa, and so it tends to be a lot of corn and soybean and row crop production. But we've been involved with some energy management type work with it. That way, I like to start off with the concept that grain prices really have been doing quite well here the last 2 or 3 years for folks, and we're all happy about that, at least on the grain side of things. If you're a livestock producer, maybe not quite so much, but oops, I'm going through the slides a little. Sorry with my advance here. Anyway, if you're a livestock producer, maybe not quite so much, but grain prices have been kind of trending up, and that's put people in a good mood that way. However, we know that energy is being consumed as we do that. That's one of the crop input issues here, and so one thing that we've been doing is trying to educate people on just the sources of energy that they use in farming operations out there. Sometimes I quiz folks with you're using electricity or using propane for drying and heating shops and livestock buildings and that type of thing, and you're also using diesel fuel on the farm. Which of these do you use the most? And it turns out, at least in the state of Iowa, diesel and gasoline use, but primarily diesel by far really is the primary driver here that way. Now this will vary a little bit by state. For example, if you look at the Wisconsin numbers, for example, that electrical slice of the pie will probably be a little bit larger as you think about some of the dairy operations and that type of thing too. But I would encourage you to look around at energy use numbers you may have that way. Prices of grains have been going up on the output side of things for crop producers, but the prices of fuels have also been trending up, and this is just a month-by-month price of diesel fuel over about the last 10 to 12 years now that way, and we know there's variation. You see that big spike there in 2008, but things go up and down, but have been trending upward, and I don't know what they'll do this year, but it certainly can be an issue for folks. The same type of information on the gasoline side of things. We're in basically global energy markets anymore, so it's been good news basically that we've been been able to up our production some here in North America, but we've got a lot of folks around the globe that have plans for that energy, and so I think energy management is going to continue to be something that people need to be thinking of. Just an example, kind of lead things off. Again, this happens to be a row crop operation, but when you look at corn and soybean production, I would say it's fairly typical that a lot of growers are using about 4 to 6 gallons per acre of diesel fuel used there, and this just might be kind of a typical set of field operations that someone might use: a primary tillage, a secondary tillage, and so on through there, and you can see how they add up. Looking at this, maybe one other issue here to kind of put this in perspective. 4 to 6 gallons per acre of energy use in the field, but sometimes people want to compare this to the amount of energy they're using for drying of field crops, and particularly on the corn side of things here. These would be examples of the energy equivalent, or about how much energy it would take to dry an acre of corn 5 percentage points, say from 20 down to 15% or something like that. Depends a little bit on whether you're using a high temperature system or a natural air or low temp system, but you know, the energy use can rival or even be a little bit greater than the field operations. That way in years that we do have grain drying. Now this is just on the corn side of things, and so for other crops, or for example for soybeans, this wouldn't be an issue, but just to give you a little perspective, and I think there's another part in the series probably coming up on grain drying that they're going to go into a lot more detail on that. Where we're headed really in this presentation over the next maybe 20 or 30 minutes or so, something like that, is looking at how we're using energy in field operations and some ways that we can maybe manage that and save some energy that way. And I won't go through the whole bulleted list there, but you can read through there. These are the points that we're going to try and spend just a little bit of time, maybe 3-4 minutes of time on each of these. You know, how much energy they're using, what we can do to manage this and put this in a little better perspective. Back to the fuel used in field operations. Another way of looking at this is just you know, how much fuel in terms of gallons of diesel are being used on a per acre basis. The bar on the clear right side of the chart here shows how much diesel fuel we're using to do planting, spraying, and harvesting operations. You have to get the seed in the ground. You have to get the crop out of the field. So plant and harvest are givens. And for a lot of people, for pest management, they go with some type of chemical management strategy, and so at least one spraying operation is pretty typical. But a lot of the tillage operations kind of listed on the left side of the chart and in the center there, primary and secondary tillage operations are ones that people choose to either do or not do. You know, does it apply to your operation or not? And it becomes kind of part of the management scheme. And they do have quite a bit of bearing in terms of energy use. You can, in a no-till system, you may be, for row crops, you may be using 2.5 gallons per acre of fuel, but in fact for any kind of tillage system, well, you can double that number pretty quickly with another 2.5 gallons per acre or more, depending on the tillage system you use. I'm sure a number of you on the webinar here are familiar with some of those fuel use numbers, but those types of things. So we encourage people to think about, you know, is that tillage operation, how well does that fit into your management plans? And we know there's a lot of issues, not just from the energy side, but also from resource conservation, that type of thing that come into play here. At least in Iowa and to a fair extent in surrounding states, ones I'm familiar with, at least in this part of the country, why, in terms of soybean production, we don't see a whole lot of response to tillage. These are average yields over about a 5-year period here at 6 different farms scattered around the state of Iowa for different tillage systems for soybean production. And as you can see, you don't want to bet a whole lot on which one's going to have the highest yield, because they're, you know, over time they tend to be dead even, and so it makes it somewhat questionable on whether those tillage passes are really doing anything for your yield or your soybean management scheme there. Again, never say never, but it tends to be kind of low-hanging fruit, or a place for folks to start that way, and maybe looking at reduced tillage passes. If you do have to do tillage, another thing to look at is, you know, how aggressive do I need to be? And this shows fuel use per gallon in terms of some deeper tillage or subsoiling operations. This actually comes from a colleague of Scott's there at University of Wisconsin, but a number of years ago, Dr. Kevin Shinners did some field work where he was looking at fuel use and corn yields, basically, from some ripping or subsoiling work, and this has been replicated in some other places. But you see, going from a tillage depth of 9 inches on the left there to 18 inches on the right, you almost double the amount of fuel you use. You go from 1 3/4 gallon of fuel per acre to 3 gallons of fuel per acre. And so again, you know, if you've actually got a compacted layer there that's causing you some yield concerns or some management concerns that way, that's one thing. But in fact, if you're just tilling deeply, you know, without that going on in the background, why it can be a real time and energy waster here too. So I always encourage people to kind of look and see, you know, manage their tillage operations, the ones they're doing, and there may be some ways to save here. So some example dollar numbers here. You know, some of these primary tillage passes, particularly as you start to get some depth in the soil, you know, 1.5 gallons of fuel per acre or more is not unusual. And so over a 1,000-acre system here, and I'm using $4 a gallon diesel price here just for the example. There's a potential if you can eliminate that more aggressive primary tillage pass, there's potential for $6,000 of out-of-pocket savings here on the diesel fuel cost. Let's look at this another way, kind of in the second part of the lower part of the slide here, but just raising the tillage depth, say from 15 inches back up to 9 inches, or perhaps eliminating maybe one of those secondary tillage passes, maybe going to just one pass with a disc instead of 2, that type of thing. Why, there's about a 3/4 gallon fuel per acre savings. So again, over 1,000 acres, we're talking about a savings in the neighborhood of $3,000 here potentially by just leaving the tillage equipment parked. Okay, kind of switching issues here again a little bit. We're going to talk about ballasting and weighting here on the tractor. And I find most tractor operators know this is an important issue, but it's one that we don't face every day or even every season a lot of times. And so people tend to kind of ignore it a little bit, but you can pay some pretty big penalties here. Optimal wheel slip on the drive wheels on the tractor, it depends a little bit on the soil situation you're in. But for a firm soil, such as that upper red curve there, you know, somewhere around 8 to 12% wheel slip is optimal. Gets you your best fuel efficiency, most efficient use of the tractor. If you're in looser soil, say a tilled soil condition, that figure moves up to probably about a range of 10 to 15% wheel slip. But again, for a lot of folks, you know, 9 to 12, 13% wheel slip is kind of what we're after. For a lot of newer and larger or greater horsepower tractors that people have purchased here in the last probably 4 or 5 years, they often do have a slip meter right on board the tractor, and that's probably the easiest way to check wheel slip that way. If you've got an onboard slip meter there, but again, you want to be probably somewhere around 8 or 9 up to maybe 12 or 14% slip, that type of deal. If you can actually see those wheels slipping on the tractor, you're typically up around 20% or more. People tend not to notice it very much until they get in trouble. So there's other ways to check, and again, we've got a bulletin on the subject that goes into more detail on sort of how to do that, but you want an optimal amount of wheel slip that way. Another important thing on just ballasting and weighting is also the way those tires interact with the soil and making sure that you've got those tires correctly inflated. You know, for a lot of over-the-road type stuff, you know, with pickup trucks, passenger cars, transport semi-trailers on the highway, we want to make sure that those tires have plenty of air pressure. But on soil conditions like this with this tractor, you want the correct air pressure, because you can't overinflate these tires, and it leads to extra wheel slip, extra tire wear, that type of thing. It turns out with radial style tires, why this can be quite a penalty for you. Bias too to some extent, but a lot of our tractors anymore use radial. These are just some case study material by a couple of extension workers over in western Ohio. They enlisted some tractor operators to do fall tillage work with their tractors with tires inflated at either 24 psi or 14 psi. And 24 psi for all these tractors was really on the high side, and you see when they got closer to the correct inflation pressure on those tires, their gallons of fuel per acre loss dropped, 5, 6, 8% was pretty common. That last tractor over on the right, the 4955, was a front wheel assist tractor. And that operator actually was saving about 30 to 35% fuel when he dropped that air pressure, and he did some more things beyond that. And again, he was way off on his inflation pressure when he started that way. But just an example of kind of fuel savings that you can see with correct inflation pressure. Those radial tires in particular, if you overinflate those, it tends to shorten the wheel track. These are just the tire print underneath the tractor drive tires of one particular tractor. We put a sheet of white poster paper underneath the tractor tire and used a can of black spray paint just to show kind of the footprint of the tire. But the poster on the left there is with the tire inflated to 28 psi. And the poster on the right is with the air let out to 8 psi. And you see just, the amount of number of lugs that are engaged in the soil there on that lower air pressure tire that way. It just really does help your traction. So, again, it's not necessarily low pressure, but it's correct inflation pressure, and you need to know how much weight that wheel and rim and tire is carrying and manage it appropriately. And that's kind of all part of the ballasting situation as we go through there. A couple other things just on tractor operation. Some of the new precision ag tools in terms of making sure that you aren't getting excessive overlap with your field passes can be helpful. Here's just a shot of a RTK base station out in the field, but just to remind folks that can be something that can help pay for some of the new hardware that they're getting and software on the tractors. For example, here's a position sensor on an older tractor for an auto steer type system or auto guidance system. But again, these things can also have some energy payback. And again, I think that's probably going to be covered in a little more detail probably in this series a little later on, so I won't go into too much depth. So what are we talking for ballasting and tire inflation issues? A fuel savings of 10% is not out of the question here, particularly for people that have not paid any attention to their tractor weighting or ballast and what that correct tire inflation should be. And I think you saw that in those earlier graphs there. But over about 1,000 acre operation and a $4 a gallon diesel cost, we're talking somewhere in the range of about $2,000 on an annual basis of savings. If you're aware of what that tractor should be weighted at and also the correct inflation pressure, it also pays to check that inflation pressure, and there's probably about somewhere in the neighborhood of a 3% savings by just getting a good air pressure gauge that'll measure within a couple of psi that way, and checking those tires every 10 days or a couple of weeks through the spring and fall seasons, that type of deal. And there's probably somewhere in the neighborhood on a 1,000 acre operation, again, of about a $600 savings that way. Okay, next topic, or getting into something a little bit different. Let's talk fertilizer applications. You may not think about fuel use with fertilizer application a whole lot, and you're not directly purchasing fuel when you're purchasing fertilizer, but there's a fair bit of energy that goes into some fertilizer products. This table basically shows the amount of energy in diesel fuel equivalent, or gallons of diesel fuel per pound, for production of nitrogen, phosphate, or potash fertilizer. And I don't expect you to remember the numbers here at all, but it turns out that those nitrogen products, those top 4 lines in the table here, they all need about 12 to 15 times as much energy to produce a pound of fertilizer as, say, the potash product in that line immediately below it. And interestingly enough, on phosphate, on MAP or DAP, it actually releases some heat during the manufacture. I'm not claiming we're making a lot of energy here, but my point being that when we talk energy and fertilizer in terms of NP and KY, it's really nitrogen that's the main issue here that way, and on a per pound basis, it's using 12 to 15 times as much energy as what our other two major fertilizer components are using that way. So what does that mean? Well, for a corn crop, it depends on how much you're applying, but say you're putting on 125 pounds of anhydrous ammonia on the corn crop. That's the energy equivalent of around 15 gallons of diesel fuel per acre. Again, you're not purchasing the diesel fuel, but that's the energy cost going into it, basically, in particularly the manufacturing process and the Haber-Bosch process for the fertilizer. For a higher rate, say on a continuous corn situation, maybe 175 pounds per acre, we're up around 22 gallons of diesel fuel per acre. So it is pretty energy intensive, and it means we really need to get the correct amount on there. And of course, there's a lot of environmental things that go along with this too, beyond the energy use that we don't have time to get into this morning. But getting on the correct amount is important. These are a couple of my colleagues at Iowa State, basically, that have put together over a number of different sites and years. You see 60 site years up there in the title for the table here, but maximum corn yields in response to different nitrogen fertilizer rates. That top line, SC, the blue line there, is corn after soybeans, and you see that that curve starts breaking off somewhere typically around 125 pounds or so, maybe 130 pounds of nitrogen per acre. That your marginal rate of return on each extra pound of nitrogen fertilizer is not too high there. Continuous corn, the break in the curve is a little bit beyond that. It's probably more like 150, 160 pounds here locally, at least in the state of Iowa, that way. But people should be familiar with what the research is showing in their neck of the woods in terms of response to nitrogen fertilizer, and use the appropriate amount. Another key here is to put it on as expeditiously and optimally as possible. We've had occasion to do some work with anhydrous ammonia here at Iowa State on just uniformity of distribution. We recommend that folks use something beyond just a conventional anhydrous ammonia manifold or fertilizer distributor if you're using anhydrous ammonia. This is an example of the vertical dam manifold. It's been out for probably 15 years or more now. Was a real step up in terms of distribution uniformity from the old open chamber conventional manifold. Even beyond that, this is a newer style manifold called an Impelicon. That we actually had a chance to work on here at Iowa State, so full disclaimer that way. But it also helps. Either one of these really is a step up from the old open chamber manifold, and this one even probably a little more so than that vertical dam. What am I talking about here? What does this mean? Well, this next graph basically shows the amount of nitrogen output we had when we had the anhydrous ammonia applicator set for 150 pound rate, and we had an 11 knife system basically we're using. And ideally, every one of those knives would have been putting right on 150 pounds. And you see that's not the case with either one of these manifolds or flow dividers, but we are striving for more uniformity, and you see that the red dots there on that Impelicon manifold getting a little closer to line even than the 150 pound line even than that vertical dam manifold. Just as an example, what you can do with a manifold with better distribution uniformity, if you took the fertilizer, the nitrogen fertilizer we were applying with that Impelicon manifold, and just cut that back by 5%, so instead of 150 pound rate, basically more like let's see, about 142 pound rate, something like that. That way, basically, this is what the application pattern would look like there, and you see even the lowest output knives here or outlets from that manifold, we're still getting more nitrogen fertilizer than the lowest outputs on even the more improved vertical dam manifold. So, point being here that use something with better distribution uniformity to make better use of the nitrogen fertilizer you are applying, and it may give you an opportunity to be a little bit more conservative on those fertilizer application rates that way. What are we talking about in terms of dollar cost here? Again, I'm using 1,000 acres here just for kind of rough numbers. Not throwing 500 acres, half that, 2,000 acres, double this number, but something like this. And I use a $600 a ton price for the anhydrous ammonia, and that may be just a little bit low here at the moment, but those prices are volatile and move around. At that rate, it's for 1,000 acres, it's about 37 cents a pound for the nitrogen. And if you can adjust that nitrogen rate back by even 10 pounds per acre, you're talking about $3,700 or just under $4,000 on a 1,000-acre system. That's also from an energy equivalent standpoint. That's over 1,000 gallons, about 1,200 gallons of diesel fuel energy equivalent. So that's what's at stake there. There's a fertilizer cost. There's also an energy cost there. And again, I think good reason for folks to take a good look at their nitrogen fertilizer application issues there. I throw this slide in just to remind folks, setting up the equipment is also an important issue, and this is just an example of a double spinner spreader on a dry fertilizer applicator. For those of you not familiar with double spinner spreaders, those spinners are basically the inner parts of those spinners are turning out toward you in the picture. And someone had mistakenly put the cupped blades on these spinners on, they put the cups for the right spinner on the left spinner and the left spinner on the right spinner. And so as these things are spinning around, those concave surfaces in the center there are spinning out toward you. The dry fertilizer granules they don't get any momentum from those spinners, and actually when this was being used out in the field, you couldn't get the dry granules past just the wheel base spread of the fertilizer distributor itself. So I only show that to remind folks, whether it's fertilizer application or pesticide application on a sprayer or use of a planter, make sure that you've got things properly calibrated and configured that way, because an extra trip is just flat out an extra fuel use, among other things, not to mention the labor and the depreciation that go along with it here that way. Speaking of maintaining equipment properly, there are some things just with engine maintenance, particularly on the tractor here, that come into play. This is just a shot of the fuel filters that are so common anymore on diesel tractors, both the primary and secondary fuel filter that way. But we know it's important to replace those on a periodic basis to maintain the engine. But what does that mean in terms of fuel economy? Well, there was kind of an interesting study done by, again, some ag engineering colleagues over at the University of Missouri a number of years ago here, but they actually had tractor operators bring in tractors locally to shops, and they hooked the tractors onto a PTO dynamometer and tested tractor power and fuel use. And then they switched out the air and the fuel filters on the tractors, and then they retested the tractor. So basically all they did was just change the air and fuel filters on the tractor. And of the 99 tractors they tested, they saw an average power increase after they switched those filters of 3.5%. Or put another way, after switching those filters, they could pull back on that throttle, go to a reduced throttle setting, and reduce fuel use by about 3.5%, and still get the same power output that they were getting before they switched the fuel filters. So that's the kind of difference maintenance can make to you that way, and probably a good estimate here in terms of staying on schedule with filter maintenance is savings of around 100 gallons of diesel fuel per year with kind of typical use on a lot of Midwestern farm tractors here anyway, that way. But the filters themselves, they don't just give them away anymore. Some of those air filters, like you see here, fairly large, but really you can make up that maintenance cost quite quickly, and that's why they have a maintenance schedule on that. You want to be pretty scrupulous on this because again, an energy boost or fuel saving boost of 3 to 4% would be pretty typical that we'd see on the diesel engines here that way. Okay, a little bit more on maintenance for those of you that are working with tractors over cold weather months, doing some livestock chores or that type of thing on the tractor. Why you're probably using a block heater with that, and I've just got an example here of using a 1,000-watt heater, and if you're paying 10 cents a kilowatt hour charge on there and you're leaving that plugged in overnight, $1.20 for an overnight use would be your energy use. Conversely, if you put that block heater on a timer and just go to using that, say, from 5 to 7 a.m. before you start that tractor up in the morning, that type of deal, well, you can knock off 10 hours there. Use that's about $1 a day. And again, if you're using it pretty much through cold weather months on a daily basis, that's $100 a season. In other words, you can pay for that timer on the block heater just for one season that way. If you're using the tractor once a month, why, again, it's a good idea, but the payback isn't nearly as quickly that way. But I find most people keep that tractor plugged in with snow and ice in the forecast, who knows when here that way. Idling time of the tractor. For a diesel engine, particularly if it's been used under fairly heavy load, why I think most everybody's father and their grandfather said, don't shut off that engine right away, and they're correct. You need a certain amount of time for that engine to cool down. Particularly a lot of engines use turbocharged or turbochargers on their system anymore, and they need good oil circulation to kind of cool down from that. But by cooling down, if you look in the operation manual of a lot of the newer tractors anymore, they're talking about cooling that engine down from maybe 1 or 2 up to 3 or 4 minutes, something like that, rather than 8 or 10 minutes. And so a long idle time is really not justified. Again, I would refer people to their tractor operators manuals here that way. But for example, for a 200 horsepower tractor that's maybe been working out in the field, idling an extra minute, 10 minutes will burn over a half a gallon of diesel fuel, and at a $4 a gallon diesel price, about $2.40, $2.50 for that extra 10 minutes of idling time. And if you do that 25 times in the spring and 25 times in the fall of the year, why, $125 a year would not be atypical here that way. So do take care of the engine, but long idles are just wasted money here that way. So in terms of kind of to recap in terms of maintenance issues here, scheduling on-time filter maintenance, the block heater, limit your cool down idle time. $400, $500, $600 on an annual basis would be pretty common in terms of savings there that way. Okay, next topic, and shifting gears, pun intended here, because we're going to talk a little bit about gear transmissions and basically any type of tractor transmission. But a lot of tractors are not used at their maximum capacity all the time out there. They're often used for lighter loads, like you see the sprayer operation going on here, or maybe you could pull say a 17-row planter, that type of deal, but in fact they don't sell 17-row planters, they just sell 16-row planters, and so if you've got one of those, again, you're not using the full component of the tractor. But lighter loads are fairly commonly found out there, and you want to take advantage of being in the right transmission gear for those lighter loads. Here's an example taken right out of a Nebraska tractor test. This was on a Case IH Maxim 245 tractor. It develops maximum drawbar horsepower of 173 horsepower in 7th gear on this tractor. That's where you get the maximum amount of power out of the tractor. But if you don't need all that power, if you're just operating at 3/4 load, say those first 2 bars on that 138 horsepower use, by shifting up a couple of gears from 7th up to 9th, you actually save about 10% in fuel economy there in the fuel you're burning per hour. This becomes even more significant at lighter loads. At a 50% load on this tractor, the fuel savings are 20% by shifting up a couple of gears. Now on new high horsepower tractors, some of them are now being marketed with kind of an onboard cruise control system, and as time goes by, you know, there's going to be some electronics that do take care of this for folks. But for a number of people, you know, just taking advantage of this, this is a pretty easy way to save fuel out there. Make sure that you're not you know, overpowering that engine and transmission that way. Now, this is primarily for drawbar load applications. Most folks that are using a power takeoff load, say on this pull type forage harvester here, why you're going to need to keep that tractor engine speed, you know, up to a certain speed, so you're at operating speed for the power takeoff there. Actually, some newer tractors just starting to appear here now. Manufacturers are starting to look at maybe decoupling the power takeoff speed from the engine speed. So if we talked about this in another 6 or 8 years, well, we probably wouldn't make a stronger statement. But for PTO loads, the application won't apply quite as well. But what's involved here, let's say that you've got a couple of lighter secondary tillage loads, or maybe a lighter planting operation that way, or sprayer over that 1,000 acres. 15% fuel savings would be fairly common. That would work out here in the example to around 0.2 of a gallon per acre. That way, and over the course of that 1,000 acres, somewhere around $800. So again, $600, $700, $800, up to maybe $1,000. Again, on a 1,000 acre operation is possible for example fuel savings out there. Okay, summarizing on some of the things we've been talking about so far today. You know, a little bit here, a little bit there. Pretty soon it starts to add up to some real money out there. And this is just kind of summarizing where we've been. But on a 1,000 acre operation, just the things we've been talking about thus far, you know, $9,000 up to around $13,000 in annual savings are applicable here potentially for folks that way. And again, most of the things we've talked about are not purchasing new equipment or purchasing new hardware to do something. It's just the way that equipment's managed, maybe the way the cropping system is managed a little bit in the case of the nitrogen fertilizer. There's some ways to save energy with virtually no out-of-pocket cost here that way. Let's shift over to away from row crops, but more to a forage operation system. And particularly in forage cutting or forage harvesting, the amount of energy it takes to cut that crop can be fairly significant. On a lot of forage harvesters, the amount of fuel used or energy used for that forage harvester, perhaps half of that may be going into just, you know, cutting and chopping that forage that way. So that really puts a premium on, you know, keeping those knives sharp as possible, that type of thing. And then doing no more cutting than is necessary. Now a lot of forage harvester folks will be familiar with the term theoretical length of cut, and you need to get that forage chopped to a certain degree of fineness out there. But know what that number is, and where possible, go with the longest theoretical length of cut, so you're not cutting through that material any more than you have to. That way, again, it's a management time scheme on this. Also, in terms of forage harvest, any forage blowers used in the operation, there's quite a bit of energy implication on the blades of that blower fan, and particularly how close they are to the housing there. And there'll be a spec in the operator's manual on this, but one way to think about this for a lot of folks, the blades on that forage blower, they should be far enough away from the housing to leave the thickness of a dime, but if you put a nickel in there, that should be hitting the nickel and knocking that around. So just that thickness difference between a nickel and a dime is kind of what we're talking about for the adjustment. But you can see noticeable differences in terms of just the energy required, say on this PTO operated or power takeoff operated forage blower here that way. Again, kind of a key energy user in the operation. So how many dollars are we talking about here in terms of energy savings? For forage harvest, you know, if we're using 1.5 gallons of fuel per acre and that cutter head's using 50% of that cutter head would be, you know, if it's in shape, using about 3/4 of a gallon of fuel per acre. if those knives are dull or out of adjustment, it's not unusual at all that they might be using twice that amount of fuel, and so we're using an extra 3/4 of a gallon of fuel per acre that way, and again can start to add up over that crop and energy use here that way. Another thing on forage harvest, as you're just in part of the management scheme, as you're leaving that swath with your mower conditioner out there, just leaving the widest swath possible, or a little wider swath if you can, and allow a little more solar drying. Take use of that solar energy that way, rather than having to use as much energy as you can with those crushing rolls or impeller blades, that type of thing too. So again, just kind of a management type issue, knowing how to set and adjust the equipment. One thing that we found helpful, at least in some of our energy management work, is to encourage people to track their energy use. You know, this is a little bit like counting calories and losing weight, or if you're trying to save money, you know, how are you spending the money, that type of deal. But actually, for a lot of folks, they don't need much of a tool just to kind of get started, and we've got a bulletin basically available here at Iowa State with an Excel spreadsheet that kind of goes into that, and I'll have a list on kind of where that is here in a moment. But the Excel spreadsheet, you can just click online on this and download that. But for example, you get your electricity bills month by month. You can load in you know, how many kilowatt hours you purchased that month. They're in line 4, line 6 of the spreadsheet. You know, what did you pay for it? What was your total cost? And the spreadsheet, of course, will calculate what your cost per kilowatt hour is. I find a lot of people that they don't really, they know what their last bill cost, but they don't know what they're paying per kilowatt hour. So this helps with that. It'll keep a running total through the year. And the same type of thing, you know, for your liquid fuel use, your diesel, your gasoline, your propane is available also on this log sheet to give people a better idea of sort of how they're using that energy out there. Energy, in terms of crop production, it's not the highest crop input there. For a lot of folks, you know, the land cost, maybe the fertilizer cost, seed cost, depends on the crop, that type of thing. They all tend to be probably a higher just raw total dollar amount. But in terms of making an input on savings on your crop inputs, energy, I would contend, is often perhaps the easiest to manage of those inputs, land and fertilizer and seed and that type of deal. You may not have a lot of choice on some of those, but energy management often depends on just how you approach the situation, how you're managing the enterprise, that type of deal, and it can be some of the easiest places to really save on energy that way. Well, I mentioned that I'd tell you where that some of those, at least Iowa State bulletins are, and we've got a website for that, the E-Extension website, that the NRCS energy calculator tool. I know a number of you are familiar with some of these sites, but I'll leave this slide up here at this point. But that concludes the major points that I wanted to go over, and I think that we're getting closer to the end of the hour. Hopefully we've got time for a couple of questions, comments, rebuttal, that type of thing. So, Scott, I'm going to turn it over to you at the moment if you're there.
Yep. Does anybody have any questions for Mark? Get my box up here in case somebody types one in.
I should maybe mention and reiterate, give people time for typing in a question, but just again, encouraging people to think through how they're using energy in the field operations that way. And then there will be some different energy management tools that almost anybody can take advantage of. I find some things are, you know, are appropriate for some operators and other operators that just won't fit into their scheme necessarily. But there's often room for some energy management savings. Again, if you just kind of take a little time, think how you're using that energy, some of these tools that may help you reduce it.
Yeah, and the other thing that I think sometimes helps farmers is to actually summarize, take their bills and summarize how much energy they use on their farm to give them a better idea of what their energy costs are and what the distribution is. Because sometimes once they see that, then they can go after the big pieces and try to trim them a little bit year to year. Well, I'm not seeing any questions, so I appreciate, Mark, your time to do this, and it's always insightful. So if nobody has any questions, we'll call it a day. And I know a few people had connection problems. We'll have a recording later on that we'll send out, so if you miss something, you can review it later and find the answer. So with that, we'll call it a day. Thank you, Mark.
Thanks for the time.